Hello, this is Mr. Huff, and I was going to go over the IPC Semester 2 study guide with you. Let me reiterate that I expect you to use this guide to build a review in your notebook that summarizes the facts, it answers the questions, it gets the definitions, you make comparisons, add helpful diagrams. You need to use your notebook as a study tool to help you be successful on the next exam. So, I know you're going to see some things in this where it says things like this. Fact, waves must have energy to travel. Don't just read it. You need to actually write it down so you will retain it and remember it and be able to call it up when you need to do so on the test. You need to be able to draw and label a transverse wave. I saw a lot of people making progress on this. You need to be able to tell me about the crest and the trough, what a wavelength is, the amplitude, and the equilibrium points, or the equilibrium point in the middle. The next question a lot of people have asked about, we'll go over this one more time in class, but imagine you have a slinky on the floor and you're making waves. And what happens to the wave if you... So we need to go to a simulation and look at this a little bit. So look at this wave. Notice the speed of the wave. As you go across, you can see it's a nice consistent speed. If I change the amplitude, this would be like shaking a slinky further and further. If I increase it, watch carefully the speed. If you look at that, it's still going the same speed. If I reduce the amplitude, it's still going the same speed. The frequency is remaining exactly the same. And because the frequency is remaining exactly the same, that means the wavelength is exactly the same. Let's check. So for this wave, I measure right here, and it's around 2.5 centimeters. And if I increase the amplitude and play a little bit, and let that stabilize and pause it again, and we'll measure again, and look, it's still exactly the same length. So changing the amplitude only changes the amount that the wave moves from the equilibrium line. Okay, so now we're going to try a change in frequency. Let's reduce the frequency. So we have a lower frequency. Notice what happened to the wavelength. Well, I need to see a whole wave here. So we'll go down here and measure trough to trough. So this is about 4.5 centimeters now. So what we see is the frequency decreased and the wavelength increased. Keep in mind that frequency and wavelength are always opposite of one another. If one increases, the other one is going to do exactly the opposite. Also notice that these waves are still traveling the same speed. We're just going to watch this one go across. I'm going to increase the frequency. We have a shorter wavelength now, but if you look at the speed here, it's still going the same speed as something with a low frequency. A change in frequency does not change the speed. So we're going to put this back at a fairly reasonable frequency. And now the next thing, so what we've talked about, changes in amplitude. We know how to change the wavelength and the frequency. You change the frequency, you automatically make the wavelength do the opposite thing. But the thing is, how do you change the speed? The speed has been the same the whole time. You have to change the nature of the medium. In this case, with this string, we're going to increase the tension. And when we increase the tension, now we have a faster wave. And if I reduce the tension, you'll see that the speed is now very slow. So the way to change the speed is by changing the medium. And if you think about the definition for the word refraction, it is a change in the velocity of a wave when it moves from one medium into another. So that's what I meant by what would happen if. Let's look at the next one. What is it called when light bounces off of a mirror? Imagine you're standing in front of a mirror and you shine a laser on it. The laser is going to bounce off of that. That is called reflection. You should make a diagram showing a light beam hitting a mirror and bouncing off at exactly the opposite and same angle. What are facts about electromagnetic waves? For this, I would expect you to have a diagram similar to this. This is the electromagnetic spectrum. Everything in this spectrum travels at exactly the same speed. They all go 3 times 10 to the 8th meters per second, or 186,000 miles per second. Everything on this spectrum moves at exactly the same speed. If you notice, there is a wave shape at the bottom. This is showing you waves that have a long wavelength and consequently a low frequency. So low frequency, high wavelength. As you go toward the left on this diagram, the frequency increases and the wavelength decreases. These little tags at the ends of this arrow help us understand. Longer wavelengths are on the right. Lower frequencies are on the right. Lower energies are on the right. On the left, we have shorter wavelength, higher frequency, and higher energy. There is a relationship between the frequency and the energy. The higher frequency it has, the more energy it has. So let's look at the frequencies up here. Radio waves, these are what we use a lot for communications. These are very long waves. Microwaves, you know what that is. You can think about the microwave in your kitchen that you heat things up with. Also, cell phones work in the microwave range in this area here on the electromagnetic spectrum. Infrared, this is what you feel when you stand next to a campfire. So as we go from right to left, we're increasing energy and reducing the wavelength and increasing the frequency. There is a narrow band, and actually it's much smaller than this, where visible light lives. The red is the lowest frequency and purples are the highest frequency, so you're increasing energy as you go from right to left. Ultraviolet, these are light rays that are above the violet color. This is what gives you sunburn when you go to the beach. X-rays are in this region here, and this is what medical technology uses to look through your body to look at bones. Gamma rays are the results of radioactive decay, and these are the most powerful, the highest energy waves on the electromagnetic spectrum. They'll go through just about everything. So that is what I mean by facts about the electromagnetic spectrum. It's going to be useful for you to recognize which ones have lower wavelengths and shorter wavelengths and which have different, how the frequencies change as you go from left to right. I will have this as a reference table for you during your exam. And we just talked about organizing the waves by frequency, energy, and wavelength. So if you have that diagram, you're in good shape. List examples of mechanical waves and compare them to examples of electromagnetic waves. Mechanical waves would be like the surface of water. It would be like shaking a rope, making a wave travel down it, like a spring shaking left and right or back and forth. Those are mechanical waves. They have to have a physical medium for them to travel through. Electromagnetic waves move much faster than most mechanical waves, and they can travel through a vacuum because they're related to a particle.